In Unit 11, we are going to be talking about probability, and to start off probability, we need to figure out how to count up large numbers. The first way of doing that is with the fundamental counting principle. With the fundamental counting principle, we are going to multiply every possible option together. So we're going to multiply together the number of ways each choice can occur. Well, this phrase might seem kind of confusing and complicated to understand, so let's go through a couple of examples with small numbers. So the first question says, how many ways can you arrange the letters B, A, and D? We're going to make what's called a tree diagram first. Tree diagram is kind of a weird name because it's going to go sideways. But we're going to start over here. I'm going to make a little dot. When I have my first option of letters, if I just had 3 letters to grab and I randomly grabbed a letter, I could get a B, I could get the letter A, or I could get the letter D. Those are my 3 choices. After I've picked that, there are 2 letters left. Okay? If I had picked a B first, the next time I go to grab a letter, I would either get the letter A or the letter D. If I had picked A first, I would either get the letter B or the letter D. If I had picked the letter D first, I could get a B or an A. And then at that point, I've picked 2 of the 3 letters. There's only 1 choice left. All right, so this is called a tree diagram because it starts small and it starts to spread out. This right here are all of my final options. I'm going to highlight that piece because technically what I'm doing is this is one option. This is another option, but that's going to be really ugly and hard to see after it's a little bit. So I'm going to count up the ends of these tree branches. I've got 1, 2, 3, 4, 5, 6 ways. There are 6 different ways we can arrange the letters B, A, and D if I use each letter one time. Now, that's not very many. 6 is not a large number, but this tree diagram gets pretty big and out of control very, very quickly. If I were to use the fundamental counting principle, I'm going to have a first, a second, and a third choice. In my first choice, I have 3 options. I could get a B, A, or a D. In my second choice, I have 2 options. In my third choice, I have 1 option. 3 times 2 times 1 equals 6. Okay, those first options correspond down here, where the black was our first option, the red was our second, and the green was our third. I'm not saying, for example, in the green third column, I said there's 1 choice. There are multiple different ways I could get to that 1 choice, but by the time I get to the third thing to pick from, there's only 1 option left. That's why there's a 1 right there. Okay? In this second example, it's going to be a slightly different scenario. Instead of just picking 3 letters, there is a series of things to pick from. So it says, as coach of the soccer team, you get to decide what uniform the team will wear. You have 3 choices of shirts, long sleeve, short sleeve, or sleeveless. 2 choices of shorts, white or green, and 2 choices of socks, black or striped. How many uniforms could you make? Well, I'll do another tree diagram. If I start, we'll go in the order of the question. I get to pick a shirt. I could pick a long sleeve, I could pick a short sleeve, or I could pick a sleeveless. I'll put this as sleeveless. Helps if I spell it right. Okay, after you pick your shirt, you get to pick your shorts. You could pick white or green. And then after you pick white or green, you get to pick your socks. You could pick black socks or striped socks. As you can see, it's a lot of just repetition, just doing the same thing over and over and over and over again. Here are all of my final options. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I didn't have very many things to pick from, but I still have a total of 12 different uniforms. if I used my fundamental accounting principle, I would have an option for shirts, for shorts, and for socks. There were 3 shirt options, 2 short options, and 2 sock options. 3 times 2 times 2 is 12, which is much faster and takes up much less space. So from here on out, I'm not really going to use the tree diagram, but you absolutely can if you are stuck on, like, I don't know how this fundamental accounting principle thing works. You can write out all of the possible options. It's just going to become very, very, very time consuming, and you'll probably miss something somewhere. Okay? Because in this next problem, we're at a restaurant where you have 8 different choices of entrees. You have 2 salads, 12 drinks, and 6 desserts to pick from. And it says, how many different dinners could you have if you choose one from each option? Well, I'm going to start with a blank for entrees, a blank for salads, a blank for drinks, and a blank for desserts. My choices of entrees, I have 8 of them. I have 2 choices of salads, 12 of drinks, and 6 of desserts. So I'm going to multiply those numbers together. If I do 8 times 2 times 12 times 6, I'm going to get 1,152 different options. Now, you could make a factor tree or a tree diagram of that, but considering how much space this one that had 12 took up, if we got to one that had 1,152, that's going to take up over your whole sheet of paper, probably. So make sure that we're getting comfortable with this fundamental accounting principle, okay? For this next one, how many different 7-digit phone numbers are possible? Well, there's 1, 2, 3, 4, 5, 6, 7 digits, right? I'm not going to write first, second, third, fourth, but you get the idea. The key part is we have to know how many possible digits there are. So off to the side here, normally people count off 1, 2, 3, 4, 5, 6, 7, 8, 9, which is correct, but there's also 0. So there are actually a total of 10 digits, but it says the first digit cannot be a 1 or a 0. So if I look at the rest of these digits, those are 8 options. So my first blank gets to be an 8, and everyone after that gets to be a 10. That means I'm going to have 8 million different phone numbers. Okay. When it comes to multiplying by tens, hopefully we've learned at some point along the lines that every time you multiply by a 10, you just put a 0 on the end of the other number. So I know there were 6 zeros to add on. The only other number was multiplying by 8. So 8 with 6 zeros. For this next question, it says students are entered into a drawing to pie one of 3 teachers in the face. How many ways can one student pie one teacher in the face? Well, I'm either going to be a student in this option, or I'm going to be a teacher. I have 773 different opportunities if I was a student, but only 3 for a teacher. I multiply those 2 together to get 2,319 different ways. Now, these numbers are going to get very, very large in this chapter, and a lot of them are going to feel kind of overwhelming and like they don't make sense. But we have to kind of wrap our head around the idea of what we are counting. Okay, it's easy to say, oh, I have 773 students and 3 teachers. Well, that just means I have 1 in 773 students, so 773 different ways for a student. Well, each of those 773 different students have 3 different ways they could get a teacher. That's why we're multiplying these 2 numbers together. Okay, we're just taking advantage of how that tree diagram works. We developed a multiplication process so we don't have to write that thing out all the time. Okay, so that's a very quick video on the fundamental accounting principle. Next up, on the next video, we'll be talking about permutations. Have a great day, everybody.